All right. Good morning, everybody, both online people and in-person people. We are in chapter 5 right now. I sent an email out to people yesterday and just saying what I'm going to be doing for tracking attendance from now on, which is nothing. What I've noticed is if you look around, there's a couple of empty seats, not too bad, but I kept increasing the number of people I was scheduling for each class to the point where everybody who indicated they wanted to come every class got on every list. And then everybody who wanted to come half the time was getting on every second list. And then everyone who wanted to come occasionally was on like basically every third list. So I've just said, if you want to come, just come, because there's so far always been a few empty seats, and it looks like that's been working so far. So yeah, you won't be getting those emails from me unless the class starts to get so full that I have to back up on that a little bit, which might happen right before a midterm. I'm not sure. Although I don't know. I mean, it's pretty much the same thing you're getting if you're online versus in person. I don't know if I have anything else news-wise to let you know since Friday. It's been quiet. We are in chapter 5 right now, talking about chiral molecules. And this is sort of the last chapter that's going to be around structure, because the previous chapter a lot of time talking about structure. We introduced the concept of stereoisomers versus constitutional isomers. We looked at different chair conformations of cyclohexane. We looked at strain, Newman projections, all these sorts of things, which are all related to shapes and structures. And this chapter is as well. Starting next chapter, we're going to start reactions. And I feel like the end of this chapter is almost like a big dividing line, which separates the beginning of the course from the second part. It's almost like you're ending the course and starting a new course. Although everything we learn keeps coming back. Even cyclohexanes. I mean, you think that's sort of a weird, oddly specific thing to be looking at, but we will be coming back to cyclohexanes as well. So chiral molecules are molecules that we said have mirror images that are not superimposable, right? That means if you take the mirror image of a chiral molecule, you have a different molecule. It's not the exact same thing. And we looked at some ways of identifying chiral molecules, and we said maybe the surest way is to find a molecule that has one chiral center. And a chiral center is a carbon atom that has 4 different groups. So if you have a molecule that has just one chiral center, you can be sure that that is going to be a chiral molecule, and that it'll have a mirror image that'll be a different molecule than itself. And we're going to explore this idea more fully throughout the rest of this chapter. And we kind of finished at this point last class talking about properties of enantiomers. And one thing that's very interesting is that almost every chemical property and physical property of a set of enantiomers is the exact same. Okay, solubility, melting point, boiling point, all the sort of properties that we've come to associate with a chemical are identical for enantiomers, except for 2 things. And I see my email buzzing here, so I'm going to just shut it off, as well as messages. I don't think messages come up on the screen, but better safe than sorry. So 2 things that make enantiomers different from one another. One is how they behave in environments that are also chiral, like enzymes or any other sort of biological receptors, right? They often can have very different effects on the body. There's one case actually that is very tragic. There was a drug that was prescribed, I think it was in the 1970s, called thalidomide. And in Canada and in many countries in Europe, it was, but not in the US, I don't think, it was prescribed as a treatment for women who were pregnant for morning sickness. And this is a molecule that was chiral, and there was 2 different forms of the molecule. And, you know, one enantiomer and its mirror image. One enantiomer was very effective at combating morning sickness in pregnant women, which is why it was prescribed. But it had a mirror image. It had an enantiomer that caused horrible birth defects. And the birth defects that it would cause is the babies would be born with basically their arms and legs were like super short. And this whole sort of generation of women were prescribed this drug, and there's this whole generation of babies that were born that have been they've been called thalidomide babies. And that's because they suffered these birth defects as a consequence of having the wrong enantiomer of that drug. And if you look at it, I mean, the commercial drug was a mix of the two enantiomers. And you could just say, well, why don't you separate them out? Two things. One is that it's very difficult to separate enantiomers from one another because they have all the same properties. So all the things you would be learning in lab, how to separate one compound from another, generally they don't work on separating two enantiomers. The second thing, even if you were able to manage separating one enantiomer from the other, the body has an enzyme which converts them back and forth. So even if you took the right one, your body would mix them up, which, so it doesn't matter if you take it pure or not. One drug, ibuprofen, is found in two enantiomeric forms as well. It has one, and its mirror image has both enantiomers. And when it's sold as a 50-50 mix. So half of that pill isn't doing you any good, but it's not really doing you much harm either. So it's a lot cheaper for them to just produce a mix of the two and give you more than you probably need. But hypothetically, if you were able to separate them cheaply, you could have half the size of the pill and still have the same effectiveness. The other thing that enantiomers will do that is different from one another, which is used a lot or used a lot in their identification, was they rotate the plane of polarized light in opposite directions. So what does that actually mean, rotate the plane of polarized light? Well, you can get these filters called polarizing filters. So if you think about light as being a wave, which it is, and you think about it oscillating up and down in one direction. So you can almost think of it like a flat sheet that has height but no width. And you can imagine it passing, and if you have a light source, you know, like a light bulb, they'll have almost every orientation of light possible represented in that beam of light that's coming. Some will be going, you know, flat this way, some may be flat this way, and every angle in between. What a polarizing filter does is it blocks out all of the orientations of light except for one. So it allows a very specific orientation through. And you can kind of see in this picture, the light that we have starting over here is in all orientations. It goes through the filter, and then it comes out only in one orientation. And if you take another filter and rotate it, you can completely block the light at that point. So the way I like to think about this is imagine light, or a photon of light, is flat like a frisbee. And imagine you have a picket fence, like this one here. The picket fence is like the polarizing filter. And imagine you build like a gun that shoots frisbees, and it can shoot them in any orientation. They could be vertical, they could be horizontal, or any angle in between. And you fire them at a picket fence. Any frisbee that's vertical, straight up and down, if you fire it at the fence and it hits the empty space, can go through. Any other orientation gets blocked. Right? So that's like what a polarizing filter does. Is it blocks all the orientations of light coming to the filter except for whichever way the filter is angled. And the light that comes out the other side we call plane polarized light, because all of the light is sort of oscillating in the same plane. And you can buy sunglasses like this. When you buy sunglasses, they're blocking light. They can say polarized lenses on them, and they're generally more expensive than lenses that aren't polarized. The polarizing ones are, in my opinion, better because what the polarizing filters do is they eliminate some fraction of the light, but they let all wavelengths through equally. So what that means is if you're looking through polarizing filter sunglasses at, this classroom or whatever, the colors tend to stay true. Whereas if you use cheaper lenses have, they just basically dye the plastic to make it absorb light. And it absorbs different wavelengths to different extents. So it makes all the colors look weird, which, whatever, if you care about that, then get the polarized lenses. I think actually 3D glasses that you use in theaters are like that too. I think the way they work is one eye is polarized like vertically and the other one is polarized horizontally. And when you put them on, the camera actually puts two images on the screen. One has light that's polarized horizontally, and one that's is polarized vertically. So when it comes to your eyes, each eye is only able to see one of the two cameras. And that allows you to get two different images, and your brain puts that together as 3D. All right, so what happens if you have, let's say, a sample of a chiral molecule in water or dissolved in some liquid, and you take plain polarized light, which is coming from this direction, and you pass that through that sample that contains the chiral molecules, it will cause that plane to rotate either to the right or to the left. This is what we say, chiral molecules cause rotation of plain polarized light. And you can see the light at the other side. It was exactly vertical starting out. It twisted a bit to the right, and that's because of interaction with one of the chiral molecules. If you have it's enantiomer instead, it'll rotate it by the exact same amount, but the opposite direction. And this is used in biology. Has anyone used a polarizing microscope before, or polarizing? Basically, the way this works is you have a light source at the bottom, and there's a filter which polarizes the light. That polarized light goes through your sample, and then you have another polarized lens above your sample, and you can rotate the two polarized lenses. And what happens is any material that the light goes through that's chiral, it'll rotate it, and you can set up your two filters so that's the only light that goes through. So what it does is it basically erases the background and leaves you only structures in the sample that are chiral. So this is what it looks like. This is cotton. Cotton is made up of cellulose. Cellulose is a large polymer with many, many, many chiral centers. And so you see this sort of like a dark background. In this case, it looks kind of purple. But then very bright, you see the structures that are chiral. Amino acids are all chiral except for one. These are all the amino acids. There's one of them, which is glycine. It's the only one of them that does not contain a chiral center. And when you find amino acids in nature, they're always just one enantiomer, not the other. So if you look at structures that are made out of protein in a polarized microscope, you can see them very bright. So this is human hair. Human hair is largely made of keratin, which is a protein that is chiral. And this is muscle tissue, and in this case, you can really see where the tissue is not. You can see it's very dark in the background, so you get very high contrast images this way. So those of you in biology, maybe you'll end up using this technique at some point. I think it's pretty cheap. Like it's like a regular microscope. You just need the two polarizing filters, top, bottom. I think I used it when I was in first year biology, which means it wasn't that exotic of a technique. So we can characterize for a molecule how much it will rotate the plane of polarized light. It can rotate it either to the right or to the left. And for many chiral molecules, I keep mixing up polar and chiral. I mean chiral, right? Talking about molecules that are chiral. the idea is if you take a certain concentration of solution of a chiral molecule, it'll rotate the light by a very specific amount. And if somebody else does the exact same thing, the exact same concentration in some place across the world, they'll get the exact same rotation as well. In other words, the amount the light will rotate for a given concentration of a chiral molecule is a constant. And it's a constant like boiling point, like molecular weight, like all these other, measures that we use to identify a specific compound. So we can measure the specific rotation for a molecule. It has this symbol, alpha, and alpha can actually change depending on temperature. So normally we define the temperature we're measuring alpha at. It's usually 298 K or 25 degrees C. And then we have the wavelength of emitted light too. So often you don't just use a broad spectrum like a light bulb, you pick a specific wavelength. And the way you do this is you just make a solution with known concentration and known path length. So the cell is a certain length. You see how much, measured by how much the light rotates, and the specific rotation is just going to be how much it rotates in that example divided by C times L, which is concentration times path length. So this is just correcting for whatever concentration you happen to use to make it standardized. And the L is the path length. So if you used a shorter or longer cell, you would have different amounts of rotation, but the specific rotation is a constant and doesn't change. So here's a bunch of chiral molecules and their specific rotation values. We have sucrose, plus 66.47 degrees, cholesterol, camphor, penicillin, Taxol, S and R bromobutane. So these are two enantiomers of bromobutane, and I think it's actually S2 bromobutane. That one and that one. So these are mirror images of each other, front back. You can think of the mirror behind one, you get the other one. You can see they have the exact same specific rotation except opposite, and this is what we see. It's actually interesting. We have digital access to all articles published in the Journal of the American Chemical Society, which is it's a big journal in chemistry. And they go back to like 1880 something, which that's 140 years ago, right? At that point in time, chemistry was very crude in the sense, like, think of everything we've learned already this year. They didn't know any of that. They didn't know how to do Lewis structures. They were missing, like, what, 50% of the elements on the periodic table? Maybe not that many, but they were missing a lot of elements. No Lewis structures, no real good understanding of bonding, certainly no understanding of hybridization. They had no access to equipment like infrared spectroscopy, carbon-13 NMR, but they did have access to measurements of specific rotation. Because all you need is a light source, polarizing filters, and that's it. And so what many of these early articles in the Journal of the American Chemical Society, we sometimes call that JACS. Many of the early articles are looking at the chemistry of sugars, and they're trying to understand as much as they could about the structure of sugars based on measuring specific rotation. So they were able to get pure sucrose and get this number. They were able to get pure glucose and pure galactose, like all these simple sugars they were able to get. And then they would take sucrose, boil it in acid, measure it again, and the number would change. And they were trying to like figure out what the sugars were converting to depending on those conditions. So this is an old technique and remains one of the few ways we're able to analyze chiral molecules. This is the molecule of Taxol, by the way. I think I talked about Taxol in an early class. This was that anti-cancer drug that is taken from the needles of the yew tree. So very complex molecule. Very difficult if you wanted to just make this thing from scratch. It's been done, but it's not easy. So optical activity is a property of a mixture or a solution or a collection of many molecules. And what we say is that a solution will be optically active if it rotates the plane of polarized light. So if you have a solution that contains a chiral molecule and not its enantiomer, we would say that that solution is optically active because it will rotate the plane of polarized light, either to the left or to the right. If it only contains achiral molecules, like let's say you just had a sample of water or seawater, sodium chloride in water or something like that, where all of the molecules were achiral, then it would not rotate the plane of polarized light, and we would call that optically inactive. That makes sense. So this is just an example, right? This is sort of a collection of chiral molecules that'll rotate the plane of polarized light, optically active. This is a bunch of molecules that do not have any chiral centers, are not chiral molecules, optically inactive. But what if we have a solution that contains a chiral molecule and its enantiomer, and they're both present in equal amounts? So it's 50-50, exactly 50-50. What happens for this is we end up with a solution that's also optically inactive. If you think about it, the 50% of one enantiomer are trying to rotate the plane of polarized light to the left, whereas the 50% of the other enantiomer are trying to rotate it back. And the net result is they exactly cancel each other out, and the light doesn't rotate at all. So we have a name for this sort of solution. We call it a racemic mixture. Racemic mixture means you have equal amounts of a chiral molecule and its enantiomer together in solution. Now, the reason we have a special name for solutions like this is the norm. This is super common. If you try to do chemistry that makes a chiral center, almost always you get a racemic mixture. I'm going to show you an example. Here's a chemical reaction that you could do. Is that a chiral molecule? Any chiral centers here? You can see that okay? What are we looking for a chiral molecule? You want a carbon that has 4 different things. So if a molecule has a CH3, that's not a chiral center. A CH2 cannot be a chiral center because there's 2 of the same thing, 2 hydrogens. And it can't be sp2 because that can't have 4 different things attached either. So this is a CH3, that's an sp2, CH2, CH3. So none of these are chiral. All right. But what you can do is there's a reaction. I think this might be an organic 2 reaction. It's called sodium borohydride. This will do a reaction that'll convert the ketone to an alcohol. Now, do we have any chiral centers? Yeah, we do, right? Right here. We often use a little asterisk to identify the chiral centers because it has 4 different things. It has a hydrogen, an OH, a methyl, and an ethyl. And so what that means is when we make this, we could make that or that. Often when you have a choice of making more than one product, the one that's formed in greater amount is the one that's more stable. Which one of these two is more stable? They're identical. Exactly the same. They're enantiomers, so they have the same almost everything. Same heat of combustion, same stability, same delta H for whatever. Same, the only two things that are different are how they interact in chiral environments and like an enzyme, and planar polarized light, which is nothing to do here. So what you'll get when you make this is 50%, 50% exactly, because there's no preference to make one versus the other. So if you do this reaction, you will get a racemic mixture. In fact, it's a huge thrust right now in chemistry to try to find out ways to do reactions like this and not get racemic mixtures. We don't like getting racemic mixtures. We want just one or the other, because if you're trying to make a drug, right, drugs typically have very different activities for one versus the other, and you don't want a mix. You just want one. So you want to be able to control which of these you get. If only, let's say they're even really easy to separate, you're going to throw away half your material that you need. And that's wasteful and expensive as well. So normal chemical methods, like probably every chemical method we're going to be doing in this course, produces racemic mixtures, which is why we have a special name for them and why we give them sort of a special consideration. If you start with something that's optically inactive, you're going to get a product mix that's also optically inactive. And this is actually something that's very interesting about biology, is biology, and when I say biology, I mean living things, living systems are excellent at making just one enantiomer and not getting racemic mixtures. And the reason that is they're made inside enzymes, which are chiral environments. So they can churn out only the enantiomer that the body needs and not the other useless one, right? Or dangerous or damaging or whatever enantiomer. So we are trying our best as chemists to mirror what biology is doing and produce just the enantiomer that we want. But unfortunately, most standard typical methods give you racemic mixtures. They're optically inactive because you don't have a net excess of one versus the other. When you do have a sample that contains two enantiomers, not necessarily in equal amounts, we like to talk about if you have an excess of one enantiomer versus the other. We have a term for this. We call it optical purity. So if something has only one enantiomer and none of the other one, we would say that that sample is optically pure, meaning it only rotates the light one way and that's it. You don't have a mix that kind of makes it only rotate part way. And we have a very simple mathematical equation to define this. The percent optical purity, somewhere between 0 and 100%, is just equal to the percentage of the major enantiomer minus the percentage of the minor enantiomer. Percent optical purity is also called percent enantiomeric excess, two names for the same thing, which is often in the literature just called percent EE. Okay. So here's a question. A sample of ibuprofen was found to contain 80% of one enantiomeric form and 20% of its mirror image. What's the percent EE? 80 minus 20 is 60. That's literally it. And that's probably the most math you're going to have to do in this course. Okay, subtraction. Hopefully that's okay. So percent EE is telling us how much excess we have. So it's almost like the 20% of the mirror image cancels out 20% of the original. And what we're left with is 60% excess. So here's a paper. This is published in the Journal of Organic Chemistry back in 2005, where they start with a molecule like this. You can see X is either a hydrogen or a bromine. R, you can see the way it's kind of coming off at a weird angle out of the ring here. It just means it could be in multiple different positions. And they make 18 different examples. And what they do is they treat it with those conditions that you see there. This thing is a fancy looking catalyst that they made, which is chiral. And what it does is it does a reduction. It turns ketone into an alcohol that you see here. And you can see this a chiral center that's formed, and the OH is going back. So they're trying to make just that one and not the enantiomer. And so they make 18 examples. The first one is the chemical yield. So the chemical yield is between 78 and 99% yield. The second one you can see is EE. So EE is enantiomeric excess, and some of those examples, some of those 18 examples, they were able to get 99% EE, which means basically they had greater than 99% of the desired enantiomer formed and less than 1% of the undesired one. So this is the sort of thing that people are really working hard, and they build these exotic catalysts. What they're trying to do with these catalysts is mimic the activity of an enzyme. Enzymes can do this very well, but enzymes are very complicated in structure. You can't really easily make a lot of an enzyme. But people are trying to make these kind of artificial enzymes like this and produce excesses of one enantiomer and not the other one. All right. So if the only way we can tell for a chiral molecule which way, whether it's one molecule, whether it's an enantiomer, or whether you have a racemic mixture, is by plane of polarized light rotation, how can you actually tell what the actual configuration of the atoms is? For example, you have a chiral molecule of 2-butanol. You could have this, or you could have this. How do you know which one of those you have? You may know you have 100% of one or the other. How can you tell whether you have the one with the OH coming forward or the one with the OH going backwards? Up to the 1950s, they didn't know. It was like they knew they had one, but they couldn't tell. So they knew, for example, if they did a reaction that didn't involve the OH, they could tell if the OH changed its configuration or not. But what happened in the 1950s? I think 1951 was the first one that they solved. A new technique came along called X-ray crystallography. What X-ray crystallography is if you take a compound and you grow crystals of it, and you can blast it with X-rays. The X-rays are diffracted, and from the diffraction patterns, you can mathematically work out the position of all the atoms. And you get an image that looks kind of like this. This is a molecule that I actually made in the lab once and had it, grew crystals and ran X-ray crystallography. And back in the 1950s, this technique was very difficult to do. In fact, to solve this structure, to find the exact positions of the atoms in one molecule would take about 4, 5, 6 years of work. And what people would do is they would set up their screen, their crystal, their X-ray beam, and turn all the lights out, whatever, and shine it. And then they'd have to know the exact angle that it hit the crystal at, and then look at the diffraction pattern, and then rotate the crystal, do it again, and then get a bunch of different rotations, and then do a bunch of math. And it was so much work. Now we have computers that can do this for us. It takes a computer about a few hours to do the same work. Which always makes me wonder, like, it used to be, if you were early on the game on this sort of work, you may start a PhD, and your PhD may be solving the structure of one molecule. Imagine if you took that person, you just finished a 6-year PhD, and you solved one structure. Or maybe you didn't even solve it, I don't know. Let's say you solved it, and then you get like beamed into the future, and there's like a machine, and you're like, oh, just put your crystal here and hit go, and then ding, it's up at like an hour and a half, 2 hours later. Be kind of a, I don't know, I guess it's the same thing. Like, that's always been the case in history. Same thing as if, you spent your whole life digging ditches with a shovel, and then like you could jump in the future and see like a backhoe just like. I felt that once actually. When I first moved into my house, we had a bunch of trees and stuff, like kind of like we wanted to clear up some space to have a backyard. And so we cut some trees down, and I started to dig at the roots, you know, the stumps, to pull them out. And me and my brother-in-law, we worked for like 3 days to pull out this big stump, and got it out. And then we kind of took a few other stumps out. And then a guy came with a tractor. He was going to level out a part of the lawn. And he's like, "Do you want me to take care of the rest of the stumps for you?" I'm like, "Okay." So he just like pushed the stumps, and they just came up, and then pushed them all to the back of the lot. It was like one sweep, and he did like 8 stumps, and then he was just done. And I was like, "Yeah, okay, that was 3. This has nothing to do with organic chemistry, does it?" Yeah, trees are organic. They got organic molecules in them somewhere, don't they? All right, so absolute configuration, we can know absolutely if an OH is going forward or going back in a sample, because we can grow crystals and stick them in an X-ray. We can get an X-ray crystal structure. We don't have one of those machines at Acadia, but there's one at SMU and there's one at DAL. So these are typically services that you send off for. I don't want to talk about that right now. Here's another Journal of Organic Chemistry, JOC article. This one is talking about the absolute stereochemistry of immunosuppressive macrolide brazilinolide A. So basically what happened is some natural products chemists discovered a pathogenic actinomycete with this Latin name. And they looked at the molecules that this thing was producing inside of its little body, and they found this compound. They isolated it from everything else in there. They used NMR spectroscopy, and they figured out what the structure was. But they weren't able to tell what the stereochemistry of all those positions happened to be. This molecule has 26 chiral centers. So you can see in this molecule, all the numbers correspond to the numbering of the atoms. So every atom, every carbon here has a number. But you can see several of the carbons have a little r or a little s by them, right? Like you can see little r, little s, little r, little r. Every chiral center in this molecule is given one of those 2 labels. And what this paper has done is it's taken every chiral center and it's identified if the subgroup, like let's look at number 21 here, little asterisk there giving you a chiral center. They figured out that that OH is coming towards us or going back away from us. And it wasn't trivial, right? I think in this case, they couldn't just grow a crystal and then determine it. They had to use different methods, which are like advanced NMR methods. And this is a not simple molecule. This is quite complex. And you can see this has immunosuppressive activity. So whenever they find molecules with biological activity, there's a lot of interest in there because, you know, immunosuppressive, we have a lot of disorders that are due to hyperactivity of immune response, like allergies or I think arthritis, rheumatoid arthritis is like a overexpression. So if you have a drug that has immunosuppressive activity, that could potentially be used to treat things like that. But what I want to come down to are these labels. They're all labeled R or S. What does that mean? We're going to find out. So these 3 guys, Kahn, Ingold, and Prelog, came along with a system to identify, if you have a chiral center, how to give it a label. Okay, so it's called the CIP system, Kahn, Ingold, Prelog. Ingold actually has some Canadian links. Ingold was a British scientist, and he did most of his heyday was the 1920s. So basically everything we learn in this course from now on was his work. So he sort of fleshed out the field of organic chemistry. He was like the pioneer. he had a son named oh my God, I can't remember his son's name. Chris Ingold was his name. It'll come to me, don't worry. But his son is probably one of the top living chemists in Canada right now. And I know this guy, which is weird that I can't remember his name. Anyway, Keith. Yes, Keith Ingold. So Keith Ingold was his son, and he started working in Canada, and he worked at the National Research Council in Ottawa. And when I was a postdoc, so I finished my PhD, and I first go to this new group in Ottawa, which was not Ingold's group, but he was good friends with Ingold. And my very first group meeting, I had to propose some research and defend my work and all this kind of stuff. It had the top two at the time, the top two chemists in Canada, based on there's metrics about how well, their impact on chemistry and so on. So he was there. I got to know him a little bit through the group, and he was in his 80s at the time, 70s, 80s, and he was still an avid water skier. So he invited the whole group over to our place, to his place, and it was funny because he had this this coffee table that was all glass, and under the glass were all of the boards that he had on one side and that his dad had on the other side. So Chris Ingold's, all his like medals. He never won a Nobel Prize. He should have, but he never won one, apparently because he was like mortal enemies with some guy who was on the Nobel Prize selection committee. But he basically discovered everything we're going to talk about in this course. So definitely based on his contributions, Chris Ingold deserves to be on there. Yeah. So anyway, this is a bit of a joke, but there was a conference where people that were interested in stereochemistry made a deal to use a new set of rules, which were the Kahn-Ingold prelog rules. You can see it was witnessed by Kahn, Ingold, and prelog. He was knighted, so that was one of the things, at least, that he had in this glass table. And of course, they agreed that they would use this set of rules, and if they didn't use the rules, the cost was they had to submit to a penalty of 1 glass of liquid refreshment to be supplied at the cost of the infringer to all stereochemists present. So very important real thing there. What are these rule systems that we're going to be looking at? Well, here you go. They propose that anytime you have a chiral center, like you have in this molecule, you can label that given a letter, which should be unambiguous. Anyone could use that label and determine exactly what the configuration of that atom was, right? Whether you had the exact chiral center or the mirror image of that same chiral center. And they used the symbols R and S, which translates to, I don't know what language they used. S is sinister. Sinister is left, and that is, I don't know, is it Latin? Greek? And whatever R was is right, Regis or something like that. Anyway, we have a procedure to tell if a chiral center is R or S. Relatively straightforward. It's one of these things that gets easy with practice, and I've practiced this many times, so I can usually just look at it and then just do it in my head. But it's often helpful to draw the thing out and determine it on paper if you are not as practiced. So what we need to do is we look at a chiral center like here. We look at the 4 things that are attached. We have a hydrogen, a bromine, a chlorine, and in this case, a carbon. And what you would do is you would rank, give a rank, assign a rank to each of those 4 things. Okay? The ranking is done by atomic number. The higher the atomic number, the higher the rank. The lowest ranked one is going to be whichever has the lowest atomic number. It's almost always hydrogen. Lowly hydrogen. Its atomic number is 1. You can't get any lower than that. So right away, if you see a chiral center and there's a hydrogen on there, the hydrogen is going to get the lowest rank. So in this case, it's pretty straightforward. Bromine gets the first rank because it's the biggest atomic number, followed by chlorine, followed by carbon, followed by hydrogen. And so the numbers that you see written in red on the bottom of the screen are the ranks of all of the atoms that are attached on this chiral center. After you rank them, the next thing you need to do is orient the molecule so that the lowest priority group is pointing back. And the other three things are either in the plane or pointing towards the front. So you can see in this instance, the bromine, chlorine, and carbon are all either forwards or in the plane. The hydrogen is pointing back. This is the correct orientation to take the next step. This also underscores the importance at this point of properly drawing a tetrahedral atom. A lot of people love to draw atoms like this. That's no good. Okay? Please don't draw chiral centers like that, or it's going to screw you up when you have to try to do these sorts of things. The dashed line and the wedged line should always be side by side. It doesn't matter which way. You know, I put it to the right here, but instead if you want to put it to the left, that's okay too. But those two need to be together. Anyway, draw it so it looks like a tetrahedral, like that. Now, once you've done this, you've oriented the molecule so that the lowest priority group is pointing back. We now forget about the lowest priority group. We pointed it into the back, and now we're going to forget about it. And we're going to only look at the other three. What we do is we go in terms of decreasing priority, in this case 1, 2, 3, and we see if that if the carbon atom is in the center, if going in decreasing priority means going in the clockwise direction or the counterclockwise direction. So you can see in this example, going 1, 2, 3 goes around that direction. Is that clockwise or counterclockwise? Yeah, counterclockwise. Need to be able to read a face clock for this to work. Yeah, so it goes around. In other words, I guess the way you could think about it, it goes towards the left. I don't know, start at the top, goes left. And that means that if it goes in that direction, it's going to be S. If it goes in the other direction, to the right, it goes R. Here's another way to think about it. Imagine this molecule, right? We have this molecule with a Br, Cl, and ethyl, and we want to turn it in that direction. Imagine instead that this is a steering wheel, and you're going to turn the steering wheel in that direction. If you turn the steering wheel in that direction, is your car going to go left or right? Left, right? Right? Left. Yeah. So anyway, if we turn this way, that's like turning a steering wheel in that way. It's going to go left. Left is S. Sinister means left. If it goes the other way around, it goes to the right, it's R. A car would go to the right if you turned a steering wheel in that direction as well. And you can do this if you have a molecule that has several chiral centers. You can do this for every single chiral center and determine if it's R or S. Now, I started with an easy example because there's other examples which are much more complicated, because you can have chiral centers in a molecule like this, where if you're going to assign priorities, okay, hydrogen is last priority, oxygen is first, but we have a carbon and a carbon. How do you rank these in priority when they're the same atom? Although they're clearly different groups, one's a methyl and one's an ethyl. They're definitely different, right? We definitely have a chiral center. how do we manage situations like this? Given that it's 9:20, this might be a great time to leave you in suspense, cliffhanger. We will deal with how to assign R and S in molecules like this at the beginning of next class. I have office hours starting in 10 minutes. Once I get downstairs, I'll get myself set up. Please jump in if you have any questions. And otherwise, we'll see you all Monday.